Chapter 6, Number 5. What is the minimum horizontal force F needed to make the box start moving as shown in the figure? The coefficients of static and kinetic friction are 0.38 and 0.27 respectively. So to make it start moving, it's going to be the static coefficient that matters the most. That one, because it's not moving. And we're going to assume that the frictional force must be equal to its maximum value, which is to say mu s times the normal force. So we draw a free body diagram, and we say there's a normal force holding the box up, and there's a weight pulling the box down. But we also have somebody pushing down, I'm going to call it F sub P, which we know is 31 newtons. Horizontally, we have that they're yanking this thing with the force F that we're looking for, and then we have it's being resisted by a frictional force. So we end up with something like that as our free body diagram. And then we can start saying, well, from the free body diagrams, we have that the sum of the forces in the x direction, we look at this as just F minus F sub F. That's a lot of F's going on there, but it's the force that we pull minus the force of friction. And in the vertical direction, it's, well, we have the normal force pushing upward, we have gravity pulling it downward, and we also have whatever this pushing force is together, that's 31 newtons. And then from Newton's second law, we have the sum of the forces in the x direction is the mass times the acceleration in the x direction, but this object is not moving. We're trying to find the force right before it moves, so its velocity is consistently 0, which means it has no acceleration and therefore no net force in the x. And likewise, it is not accelerating up or down, it's just sitting on the table, so it has no net force in the y. So then we put these things together. We can say that F minus the force of friction is 0, and that the normal force minus the weight minus this pushing force is 0. This tells us that the normal force is however much we pushed down plus whatever the weight is, which makes sense. The normal force has to resist both the tendency to move through and also the fact that we're pushing extra. And then over here we have the force to the side has to be equal to the frictional force. So the force to the side is equal to the frictional force, but if it's just about to move, which is what we want, if this is going to be the maximum, if it's the minimum to make it move, it must be the maximum before it moves. Kind of weird, but there you go. So it must be, this is my value of F that I'm looking for is the largest force it can possibly be before it moves. And so the frictional force must be its maximum value, which means it must be mu s times the normal force. So it's mu s times the amount we're pushing against plus the weight. So then we say it's 0.38 times the 31 newtons plus the 25 kilograms times 9.81 meters per second square, which, by the way, is going to totally dominate that. That 31 is not going to be all that important. And we get 0.38 times all that stuff. And we get 104.975. But then we say, well, we only have 2 digits. So this is really 100 newtons. Note that this is really, since we want to preserve 2 digits, there's a weirdness here. This is really like 1.0 times 10 to the 2 newtons, so we can make sure our sig figs. And then Walker, because of who Walker is, he likes to write this as 0.10 kilonewtons. Again, just to emphasize the 2 sig figs.